Okay, so this is this screen recording will be uploaded to the YouTube, and so you will see the really clean version of what is shown up here. And I'm just projecting this one to the screencast using the webcam so that you guys can see through the WebEx. But this actually recording that you guys see here will be uploaded in a more cleaner version. So let me go back to the question before. The student asked about, okay, the CH4, NH3, H2O, and HF. And this is an acidity comparison. And this is actually quite important, which one is more acidic. And this one, you actually give, this question is underlying question that, okay, so this is a methane, and what about losing this one of the hydrogen here, right? And this is an ammonia. What about losing hydrogen here? This is a water. What about losing the hydrogen here? And this is an F. This is losing the hydrogen here. So this is losing the acidity means their tendency to lose a proton. So this is what is acid is about. And then naturally you are going to have this something called conjugate base. This one is essentially CH3 with the negative charges on carbon, right? And this is an NH2 with negative charges on the carbon. And if I even show the lone pairs, and this is what it looks like, and this is an OH. Typically you put OH minus, but the negative charges on oxygens, and this is a lone pairs there. And fluorine is just a negative, and it is like this. So this is a conjugate base. And you're going to compare the stability. Stability-wise, this is stable. And if you look at that electronegativity differences, oxygen is more electronegative, so it is relatively more stable compared to the one in the carbon ion. I mean, it's almost odd for me somebody to say this is an acidic, right? This proton can be taken away. We are just considering the scenario that when this proton is taken away, and what will be their conjugate base, and how stable it is. This is a very, very unstable, right? So that's why this is an increasing the tendency to have more stable conjugate base. That means it is more acidic. Okay. And the question that also posted, what I talked to you about, is this number 21. And the exam 2, spring 2017. This is something that I'm going to continue to solve. I hope I can go up to there, but maybe not. Then I will do it in my noontime. But you guys can look at my recording. The short answer for this is not a good problem. Poor wording, okay, and so you cannot get that answer like that. So it is something that I'm going to discuss and I guess criticize the way the problem was written. Okay, so let's go back to the exam. So I have uploaded question 1 to 10. So now I'm continue to solve the question number 11 from today, and then let's see how far we can go from here. And you guys ready? I hope you guys doing okay, right? Everyone is doing okay. Okay, so let's focus on this problem, and you can send any question in the chat, and so I can answer that. So this is a question number 11. This is a question about asking pH and the solution of calcium oxide and with that concentration. So this is a concentration of calcium hydroxide. Okay. So this problem is not difficult, but it's a little tricky because what you need to do first is, okay, this one dissociate calcium. I know it is a calcium 2 plus because in the second column, alkaline earth metal. And so therefore, 2 times OH minus. Right? So that's the scenario. You are generating actually 2 OHs there. So therefore, if you have a 7.0, 10 to the minus 3 molar, and you use them all, right? So this is, I mean, somebody can do this ICE. You don't have to do that. It's so, the concept is simple. But you using all this, all of them, and you're going to generate the same amount of 7 to the 10 to the minus 3. But this one, you're going to have a 14, 10 to the minus 3, which is twice of original concentration, right? So therefore, the concentration of OH minus is actually 14 to the 10 to the minus 3. Well, you can do 1.4, 10 to the minus 2. So from here, you guys can calculate POH, which is minus log 10 OH minus. And that gives me 1.85. And then what do? pH is 14 minus 1.85, and that will give me 12.15. So this problem is solved. Okay. Okay, so let me move on to the next problem. This next problem is about what will be a pH for the solution. So let me make it a little bigger. Okay, so what's the pH of this solution? So this is a acetic acid. Ka values are given. Okay, and then this one I need to move it up. So then the Ka values are given. So this is a weak acid equilibrium. In this case, you have to use an ICE, and they ask you the pH. So, keep that in mind, pH. As long as I know my H plus concentration, or POH, I can figure this one out. And the problem they give this one to here, just like that. So this is they give you a pKa value. So this problem is, also tricky in a way. They give you a pKa value for this. So if I put it in normal form, that's a weak acid, right? So this is your H, that's your A part, okay? And what you see here is a sodium plus A minus. So that's the one. So they give you a conjugate base initial condition. So you do want to have your conjugate base, CH3CO2 minus and H2O going in, and then the CH3CO2H plus OH minus. Okay, so from here, because the condition is given as an initial condition here, you want to use this as an equation to solve this. So then what is the situation now is, okay, I have a 1.60 molar concentration in my initial, and I have nothing there, and I have changes like usual, right? I'm losing some, but it's going to be small, the small values, and there will be X, and there will be X, and it will be 1.60 minus X, and this is an X and X. So I come to so far, but now I come here to find out this is a value for Ka, but what you have written here is essentially Kb, right? The base equilibrium constant for their conjugate base. So what you need to do is something that, okay, I gotta find out what is my Kb, and if you're looking at your reference sheet, so let me find out the reference sheet. Where is it now? Okay, so if you go to the reference sheet, the reference sheet among this, there is something that about, okay, so do you see that Ka, Kb is Kw, right? So the weak acid and their conjugate base, the equilibrium constant multiplied, it will be a Kw, and the Kw at room temperature is 10 to the minus 14. So I'm going to write it one more time, like here. So from here, A is given 1.8, 10 to the minus 5. And then we know the multiply by Kb is a 10 to the 14. So therefore, I can calculate my Kb here. Kb here, if you do that, there will be 5.56 to the 10 to the minus 10. Then now you are in business. Okay, so this is a Kb value that is really appropriate for the ICE situation that you have established up here. And then what do? You're going to write the, okay, so I use quite a space here. So let me just use up here, okay? So Kb is 1.60 minus x to the x square, right? And that's the 5.56, 10 to the minus 10, okay? So the problem gives a Ka, but you need to calculate the Kv, and then once you calculate the Kb, and it's easy to establish the IC problem now. And then we do our usual assumption. X is a very small value, so this is a negligible. So I'm going to neglect that. So therefore, x squared is 1.60 times 5.56 to the 10 to the minus 10. And then x is, which is now OH minus concentration. And then you will find out OH minus concentration is, you have to do the square root on this value, and that's a 2.98, 10 to the minus 5 molar concentration. From here, you guys can calculate POH, right? Take the log value, which is a 4.52, and then you guys can calculate pH, which is a 15 minus POH, and the value for this is 9.47, and that's where we are, right? So this problem is essentially knowing what you have, and once again, I'm going to highlight that this form of conjugate base. This is a conjugate base is a given, but the problem was given to you as an acetic acid, which is an HA form, right? So then what you need is Kb, not the Ka. So you need to just convert that using this relationship at room temperature. I guess that this problem is not sufficient. They must say that this is it at room temperature, but it is typically assumed if it is not mentioned. Okay, so let's move on to the any questions so far? Everyone looks good. I hope it's good, doing well. So let's move on to the number 13, and the question is what salt will dissolve in water to form acidic solution? And this is an aluminum trichloride, and if you look at the aluminum trichloride, is an AlCl3. It's actually react with 3H2O. They'll form aluminum OH3 with 3 times HCl. Okay, and you know the aluminum like to have a 3 plus. That's because that's where the columns are located in the periodic table. So aluminum preferred to 3 plus, so they can form the product, and they ended up with getting this HCl, usually a gas that coming out. Okay? So this is to make this one is an acidic here. Okay. The other one is less acidic, so we'll move on to the next problem. Okay, so this is looks like what is the pH of this solution? This one looks funny way, but that means H2Se. So you can think about it. This one is more like H2A, which is a diprotic acid. Okay. So diprotic acid, you can have a K1 value and K2 values. Okay. And then they're asking that what is the pH of concentration of this compound, right? Which is this compound, which is the original compound, and then they'll give you a diacidic constant. This problem is actually very similar to the discussion problem that I just posted up with the telluric acid. So if you have that, have follow up, that will be the one. So the pH is once again, I need to figure out my concentration of H plus. Okay, so let's do that. So let me write the equation one more time. So H2Se dissociate to give out proton, and you ended up having HSE minus. That is the first Ka, right? First equilibrium for acid. And once you generate HSE negative ion, they dissociate again to generate H plus, and this one is now Se2 minus, and that's a Ka2. Okay, so let me see. Just for the extra information, if you look at the periodic table, now what you can see here, you guys can see that the selenium is on the next to the bromine. So they prefer to can have an S2 minus, and you can kind of know that, anticipate they can have a S2 minus ion. At any rate, so think about, look at the numbers. I'm not giving you the actual, the big numbers here, but yeah, let's write it. 1.3 times 10 to the minus 4. And this is a 1.0 times 10 to the minus 11. So these both are very, very small, right? You can think about that's a ratio between the top portion over the bottom portion. So through the first equilibrium, you generate some amount of this, and you generate some amount of that. At that amount, now carried on to generate some more H plus and some more over that. So the concept here is I want to know my concentration of H plus. So H plus can come from both sides more, but the idea here is here from the beginning, 0.5 molar, you generate, so you have $1 million and you generate $10 here, $10 here, right? So that's because it's so small that you generate small amount. And once you have $10, you have 1 cent and 1 cent, right? So therefore, $10 and 1 cent, I would just keep 1 cent, and that's I would say it is good enough for me to think about it, right? The concept here is H plus is an H plus coming from Ka1 and H plus from Ka2, right? But this is so small, nickels and dimes, so I will just assume that this is a 1. So I can just focus on the calculate H plus and calculate pH from here, and then I will get an answer right away. So this is the same kind of concept that the dominant concentration contribution towards an H plus is from the K1, so I'm going to focus on that. So having said them all, what I need is I just need to concentrate myself on the first problem, first equilibrium. Okay, so that's the what I will do, and let's do the ice problem now. Okay, so this is then it will be actually not a once you understand the concept. So initially you have 0.50 and you have nothing. So, and the changes, you are going to lose some because the equilibrium will generate some. So that's an X and X. And the E is 0.5 minus X. This is an X and X. Now you're getting the usual, right? Ka1 is 0.5 minus X and X squared. And I want to know my X squared, which is a concentration of H plus. So that's, and then, okay, so from the 1.3, 10 to the minus 4. And then I can do the, like usual, well, compared to 0.5, X should be very small because this is a weak acid, right? So this is a Ka value is small, so this is a weak acid. So you need because weak acid. X is small. X is very, very small compared to 0.5. And we'll check about that once you calculate the next. And then the problem becomes simple. X squared 0.5 with 1. Okay, 0.5 equal 1.3 10 to the minus 4. So for X is, where's my X? X is now, okay, so X is 0.00806 mole. Okay, so that's an H plus. Okay, so then like I said, this is from the Ka, but that will be sufficient enough for me to move on to the calculation of what will be the pH, because this is from Ka1, first equilibrium. And so then my answer is minus log H plus. You plug that in, and you will get 2.09. Okay, so this is my answer. Okay, now number 15, and this is actually quite similar to the question that was asking before. What will be the strongest acid? And the answer is, okay, let's have a look at it. Oh, it all has an H's here, right? So what I need to do is I'm going to write down HO minus, HS minus, HSE minus, HTE minus, and then F minus. So these are the series of the conjugate base, and we're going to look at them. And then I can see that this is there is a certain kind of the groups you can see. So let's look at the periodic tables. And if I show you the periodic tables here, if you look at that, now oxygen, sulfur, selenium, and tellurium, and so Te is the largest one. So if I kind of draw some kind of a diagram here, oxygen is this small, sulfur is this big, selenium is this big, tellurium is this big. And so if you need to have negative charges on this is much more like a dispersed. So among these four, this is more the most stable. Right? And then now I need to compare that with the fluorine, and then the negative charges can be spread out this big versus fluorine is really tiny small. So this is actually, that's why the HF is not, if you compare that, HF is not a strong acid. It's actually considered to be a sort of weak acid. Okay? As you all know, HCl is a strong acid. And the same argument here, fluorine is really negative small, and chlorine is this big, and you have a negative charges. It's much better, the stability of a conjugate base on chlorine minus versus fluorine minus. This is much more stable, so that's make it this one to lose H plus to form Cl minus. So same here. So that's why the answer is H2 telluride. Okay, moving on to the number 16. This is actually the same problem that actually we when we met in the classroom, I talked about the acidity differences for this organic compound. And so the answer here is you can, if you look at here, all you gotta do is, okay, so which one is more acidic? And then you're gonna look at the scenario. Okay, so this is a compound that will form oxygen minus. That's the conjugate base form, right? And that's the number 1. And then this is the number 1, H1. And for the case of H2, after losing this, you're going to form like this. So this is a conjugate base. And then remember that, okay, so if you have this surrounding oxygens like here, it's like you have a nice kind of a pull and push scenario. These two, I have too much electrons here, so let me share that, and that can be just pushed to the other electrons. So by doing so, you ended up having double bond, oxygen, and then now negative charges was over here and here. And in my class, I also said in the organic chemistry, if you take it in your second year, and I think your instructor is all going to be likely to use, okay, charges are being spread out, negative charges like this. So this is essentially what is called a resonance state. So resonance stabilization, the negative charges are spread around, and this is a beautiful thing that this is making very, very stable, right? So what that means is this is easier to lose. Okay, not this, easier to be lost. And so therefore, hydrogen 2 is more acidic. They would love to lose this, and because of the resonance stabilization. So that's the answer, and I think you should know it by now. Okay, so this is quite frequent. It's repeated here, and it is also repeated in the other problems that we show. Okay, so moving on to the number 17. So number 17 is if you're looking at here. Which is following is true if the pKa value of something is shown up here and the pKa, and they show up these two. So you need to really develop some ideas about how this is being written. I'm going to actually spend quite some time here. So if you look at here, my starting point is actually looking at sodium, right? Sodium is a plus, so whatever is left will be a negative ion. So it means a CHO2 minus. So that's the compound that will be a conjugate base, and with what do you see? And what you see here is CHO2. I'm going to use the same color that is shown on the right, and then let's say I'm going to write an H. Do you see that now? So it is essentially mixtures of compound that is HA and A minus. So that's the thing that you need to figure that out. Okay, this is an HA and HA minus, which is a mixtures. So that's one, and this HCHO2, which is typically, I don't like the way that it's written. This compound is formic acid. And that's the actual chemical structure. It looks like that. But what can you say? This is the way it's written. So we can just deal with it. At any rate, and now I identified it is mixtures of weak acid and their conjugate base. That is what we call buffer, right? And you remember the buffer solution equation, and you don't have to remember the buffer solution equation. Show you. This is going to be very useful. I post some more of my comments on my internet the Google Docs, but it's also the same thing that you guys can see that. So let me see that. Okay, brighten up. Okay. So if you're looking at here, there's a bunch of equation. The one that is going to be useful is this. pH equal pKa plus log A minus A over HA, the ratio between A minus and HA. And so that's for the buffer solution when you have pKa values known. Sometimes actually you need to use this one, and then I've seen that some exam problems actually you need to use that. But the point is, when you have an acid and a conjugate base existed, and then you can predict the pH. If the pKa value is known, or pH, you can calculate your pKa value. This is a case where your base and your conjugate acid and your pKb is known, and your pOH is related to this. So I'm going to use the first part of the equation here. Okay, so turn it off. Okay, so this one is now currently. My handwriting is a little bit tilted. Okay. So what that means is, I'm going to write it one more time. So let me copy down what you just see. This is an equation that is going to be very powerful, and then you need to use it for many problems down the road. So this is a buffer solution equation. I also call HH equation. And what they see here is, okay, I give you the scenario where the pKa value here is 3.74. And the pH of the solution is 3.89. Okay, so then I'm going to write it as 3.89 is 3.74 plus log A minus HA. So I just finished that. And then which one is bigger? So this is a bigger, so I'm going to subtract that, these numbers, and then you will get, I don't need to calculate actual numbers, but let me pull up my calculators, and the 3.89 minus 3.74. Yeah, that's a 0.15, which is a positive number, which is a log A minus HA. So then what that means is, because this is a positive number, the A is larger than HA, right? In other words, A over HA has to be bigger than 1 to be the positive. Remember the calculus days? This is a log x and an x, and there's a plus and there's a minus. This is a graph. Remember that graph? And that's where the ratio is 1, and we are talking about the positive value here, right? So therefore, x has to be bigger than 1, so the ratio is bigger than 1. So, having said them all, this is your conjugate base, A minus, and this is an HA, right? So that's an A is your answer for that question. Okay, moving on to the next problem, which is another. Now this one says is a buffer solution, and the buffer solution is, okay, I don't know whatever it is, though, this acid, so you're just going to write it as HA, that's a concentration, and then the sodium pyruvate, which is on sodium plus A minus, right? But what is really given to you is on this A minus concentration. And they give you a Ka. So this is a probably most straightforward one, so we can finish it in no time. So let's write pH pKa plus log HA A minus. So this is an equation you can copy down from your reference sheet. And then let's say pKa value. Okay, so pKa is not given, so I need to calculate it. So pKa is minus log Ka. Yeah, plug in the numbers, minus log 10, right? And 4.1, 10 to the minus 3. And that you will get 2.39. So 2.39, here it is. And the log, what is my concentration of acid? That's an HA, which is going to the bottom, 0.05. And the 1 goes up, 0.045. You already kind of anticipate this ratio is lower than 1. So the pH value should be, this whole log value is going to be negative. So smaller is a negative value. So the pH value will be smaller than that, 2.39. At any rate, you calculate, plug in your numbers, and you'll find something 2.34. That's your pH of buffer, which is a mixture of these two, right? The buffer is always a mixture of weak acid and the weak, they are conjugate base, okay? So the compound. So answer is, for this is C. Here goes one more time. The number 20, no, number 19. This is a 1 liter buffer solution, HF, and HF Ka value is here. So this is why the Ka value is 10 to the minus 4. So it's a small enough that we call HF is a weak acid. But it's not really weak. It's kind of weird weak acid. It's kind of very dangerous to deal with HF. Okay, anyway, the HF is here, and the conjugate base, F minus concentration is given. And then what's the pH solution after the addition of, so this is how I guess a variation of problem. Addition of 100 ml of 1 moles of HCl. So then you need to consider the fact that the addition of HCl will be used used to generate this will give you an H plus, right? So the sum of an F minus will be regenerated into an HF. It is more like a going back and forth between the H and H minus. So now we need to write the equation and trying to solve in an ice problem. Okay, so this is a little more difficult, but we can do it. Okay, so HF. Okay, and then that's an H plus, F minus. And in the beginning, and I am going to write down not in terms of mole, but let me just consider this is just a number of moles here. Okay, so this is you have a 0.25 mole. And I will say, you don't put anything from yet, and then you put 0.25 mole. So this is how much you put it in the beginning. And then I'm going to write it as changes, and you're going to say, okay, I'm going to put 0.1 mole, right? So if you look at that's the amount of the H plus you added in. So you are going to add that in for that scenario. And actually, there are many ways of. That's why I'm kind of slowing down. Well, I will just say that, and I need to consider this for the way that is how the change is going to happen. So for this one to disappear, I'm thinking about going to the reaction the other way. So this changes is more. Okay, I'm gonna lose this all of them. Therefore, I'm going to take my company with me, which is a 0.1 mole, and then you're going to generate 0.1 moles of HF. Okay, so that's you have a sort of a double initial conditions in a way. You can think about that way as well. So then at the end, what you have is, this is important for you to know, is what the key information is: 0.35 moles of HF, and you have nothing, or almost nothing, right? And then you have a 0.15 mole. So that's your concentration of HA. This is a concentration of A minus for a given this scenario. And I can quickly calculate my pKa value, and the pKa value here is 3.46. So then I have all the ingredients that I have. After the reaction, by adding this H plus, you are going to, because this is a reaction, and cause to lose that H plus by combining H plus with F minus to generate HF in that form. Because it's a Ka is a small values, that means HF is a predominant form, so they like to go back to the HF. That's the justification for losing all H plus into a form of HF. And then let's calculate the pH. Okay, pH is pKa 3.46 plus log A minus, which is 0.15, 0.35. So that's essentially boils down to this end, and then you will get 3.09 as your pH for this scenario. So that will be the case. Okay, so I didn't come to here this far, but this is not a good problem. I am going to solve it at the noon class, and I'm going to put it on my YouTube video. But number 21 on this spring 2017 exam 2 problem is not a good one. The wording is poorly written here. But I can solve it up to the 20, and then I can start my noon lectures on from the 20 again. And this one is actually pretty good. Which one best describe when you have a weak base, right? This is when you have a weak base, is titrated HCl, right? So by adding HCl, right, the scenario is more like you have an HCl drip it in to the weak base here, right? This is a weak base, and you have a HCl plus is strong acids being added on. So you are destined to, your pH will go down, right? The more you add a volume of HCl solution, and then this is an equivalent point at which you will have a complete, this is the one that you have a lot, you will have a complete conversion. So essentially complete consumption, or we call depletion. Okay? So now you have a form of an HA in a form. So because of at this moment, what you have in your hand is essentially all the H minus are gone, and you have left with an HA, which is a weak acid, and that weak acid can generate a little bit of H plus with a regenerated A minus there, but this is more like you're putting on acetic acid or the very weak acid in that, I don't know, acetic acid or weak acid. Yeah, so you put it in there. So therefore, it will be an acidic solution. Acidic solution means pH is lower than 7, right? So till we less than 7 at the equivalent point, and that's an answer for the B. Okay, so on the test, on the test, will there any values of x where we can use an assumption x is very small? Or will there any values of x where we cannot use? Is it okay to just every time? Okay, so the Abby asked a question to, well, sorry, Abby, I need to, but anyhow, the A student asked, answered the question. Yeah, this is the assumption about okay, let me stop this. So I'm gonna, because this is mainly about